Okay, brilliant. Okay, so welcome everyone for this another academic year of Global Poisson. And our first speaker is Damien Calaque from Montpellier, and he's going to tell us about shifted symplectic reduction. So go ahead, Damien.
Thank you very much. Thanks a lot for the invitation. So I'll be talking about shifted symplectic reduction. Like the first part of the talk will be about general things about reduction in shifted symplectic geometry, and it is very much like now. I don't want to attribute it to anyone because that has been the result of the work of many people working in this area. In the second half of the talk, I'll talk more about the joint work with Mathieu Anel, which is about shifted symplectic reduction for derived critical loci. And I say, what did I say? So let me start with a motivation. So my personal motivation for working in this was to understand some aspects of the classical BV-BRST formalism. And so let me fix some notation. So first, let me start with a function on some space X. So I work in the context of algebraic geometry. So for me, X would be an algebraic variety, or even some more singular object like a stack or even a derived stack. But it doesn't matter so much at this point what X is. If you want to think of a smooth manifold, that's perfectly fine. And F is just a smooth function on X. And assume we have a group. So let's say, like in my context, that would be an algebraic group. But if you're more familiar with differential geometry, a Lie group would be perfect, acting on X. And assume that F is G invariant. Okay. So in particular, it means that F descends to a function on the quotient stack, a function that I'm going to call F sub red for reduced. Okay. All right. And so there's two procedures when people do the BV formalism. So I'm going to talk about the BV formalism for group actions. This works pretty well if you have more general symmetries that like groupoid or algebraic symmetries, and you might have higher symmetries like L infinity algebraic symmetries. That would still work, what I'm going to talk about. It's just like having group symmetries make things easier to state and phrase. So here is what people usually do, and there are two procedures. So let me do it in local coordinates so that things are like a bit more algebraic and easier to follow. And that's a bit also how people think about it and do it in general. So let's pick some local variables, x1 to xn, so local coordinates. And there's a game of adding new variables or new fields, if you want, to the algebra function on our space X. All right, so there's two procedures, like let me call one A and the other one B. So the first one, people usually add anti-fields variables that you would call like psi1, psi-n. So there's as many anti-field variables as like variables we started with. And these ones, they have degree -1. Then people, they start adding, like, I don't know. I mean, I usually call them anti-ghosts, but I was told that that's a bad name from the physics perspective. So you could call them anti-fields for ghosts. Let me call them like eta1, eta k. These ones have degree -2. All right. And then, like in some papers, they strangely add the ghost variables after the anti-variable for ghosts. If you read the paper of Felder and Kashdan, for instance, on the classical BV formalism, that's typically what they do. And they had like dual variables to this, y1, yk, and these ones have degree 1. All right. So that's one way, and then they extend the function f to a function that depends on all these variables, and they introduce some shifted Poisson algebra. I'm not going to talk about it right now. So that's one side of the story. Let me mention that this side is like it works all the time. So it always works, even if you have like on-shell symmetries. So namely, if G only acts on the locus of solution of the Lagrange equation, and not on the whole space. There's another procedure that only works if you have off-shell symmetries. Which goes as follows. You first add the Gauss variables. So you first add the y1, yk, and then like that's a more, that side is more what people do usually, I don't know, like most of the time, like more mathematically oriented people would do that one. So you call them Chevalel generators. Then you would add the anti-fields. Psi 1, psi n. You would call these causal variables. And then you would add the anti-fields for ghosts. Like eta 1 to eta k. And you would rather call them like Tate variables. All right. The whole point of the talk is to give you like a kind of general context when like adding these new variables has a geometric sense, and the fact that what we're doing on both sides is essentially the same thing. It will be a theorem saying that two constructions give the same results. All right. So I can actually already give you the somehow the idea. Like in this procedure B, what we're doing by adding the Chevalel generators is we're taking the critical locus of F, maybe in a derived way, and then we're doing something to this. So adding the anti-fields. No, I'm sorry. Like I missed the story. So like the stories. So the B side, it's kind of easy to understand. So by adding the Chevalel generators, it means it's a way of quotienting by symmetries, maybe in a homotopy way. So that's first taking x to x mod little g, where little g is the Lie algebra of big G. So it's kind of quotienting by infinitesimal symmetries. Then like because the function is invariant, it still define a function on this quotient space. And then adding the causal generators and the Tate's variables all in the same way. That's a kind of taking a critical locus for this space. So that's taking the critical locus of F red. So that's what happens on the B side. And on the A side, there's a bit of a different story. When you add the anti-field variables, it seems that you're already taking the critical locus of something, which is F. And it seems that by adding first new anti-fields, it means that you're taking zeros of something again, and then quotienting by something by adding the Gauss variables. So taking zeros and quotienting, it looks like a reduction procedure. And actually, on the A side, what we have is one can show, we will see this, that there's a kind of moment map associated to the derived critical locus. It has some cohomological shifts. And the space we are constructing is a symplectic reduction of this guy. And essentially, the main theorem I'm going to state at the end of the talk, it will say that there's a moment map on the critical locus of F. and its reduction is the critical locus of the function defined on the quotient space, right? So it's a bit similar, if you think about it, to this fact that the cotangent to a quotient space, that's a symplectic reduction of the cotangent of the space we started this with. So if you think about it, that's a bit that on the right, you would have the cotangent of x mod g. And on the left, you would have the cotangent of x. It comes with a moment map. And then you can take its reduction. And the reduction of the cotangent of x, that coincide with the cotangent of x mod g. Of course, this type of theorem, they only hold if you have like nice enough assumptions. If you do everything in the derived context where you don't have to care so much about smoothness, and you allow for stacks and even derived stacks, this statement becomes true all the time as soon as you assume that x would be an Artin stack, for instance. All right. So I will start with a short recap of about shifted symplectic structures first. So maybe let me say why I'm introducing shifted symplectic structures. So I want to talk about symplectic reduction somehow. So I have to tell you about symplectic structures. And if you look at what we have with variables on both sides, you can notice that we have variable x1 to xn, and they have conjugate variables xi1 up to xin, and the same for the ghost variables. So you have y1 up to yk, and eta1 up to eta k. And so we have a pairing. So somehow we have a kind of symplectic form, which is sum of dxi dxii plus sum dyi wedge d eta I. And you see that the x variable has degree, they have degree 0, the xi degree -1, the y, they have degree 1, and the eta, they have degree -2. So overall, this kind of symplectic form, if you can make sense of it, it has global degree, cohomological degree -1. So I want to be able to talk about symplectic symplectic structures, maybe reduction for things which have a, like for symplectic form, which have a cohomological degree which is maybe not 0. So that's why I'm now doing kind of this detour through shifted symplectic structures. All right. So let's start with some space X. So the correct technical term is a derived stack, but that doesn't matter so much. So if you're more used to things like Q manifolds, for instance, that is perfectly fine. The only thing that I care about is that the algebra functions on X. That's something that's it's a DG algebra, and it can have degree both in positive and in negative positive and negative range. So there's a complex which is the derived complex of X. So this complex is as follows. So so it has a lot of structure, but the underlying complex is just the global section. I'm taking symmetric powers of the cotangent complex of X shifted by -1. So by the cotangent complex, so that's an algebraic geometer notation. That is just, think about the cotangent sheaf. That's perfectly fine. The only point is that if X is a derived stack, then OX would be, again, a DG algebra, which may have positive and negative degree. So this LX, it's a complex of OX modules, and it may have degree like everywhere, right? So we shifted by -1, and that's what we defined as the derived complex. And these things comes with two gradings. There's a cohomological grading that I will call the degree. That is just the fact that OX is graded and LX is graded, so everything is graded, right? That's come from the fact that we have an internal grading everywhere. But there's another grading. That's the grading by symmetric powers. Okay. This one, I will refer to it as the weights so that I don't mix them, right? So like you may have something that has cohomological degree. So the weight is just the number of symmetric powers that we have. You may have something of arbitrary weights and arbitrary grading, and they don't need to match. The only case when they have to match all the time is the case when X is on a smooth manifold or smooth algebraic variety. In this case, this Lx here is concentrated in degree 0. So when you shift it by -1, it's in degree 1, and then the weight and the grading they coincide. But that happens only when you have a smooth manifold or smooth algebraic variety. And then there's also two differentials. And these two differentials are as follows. So there's the internal differential, the fact that OX is a complex, LX is a complex. So that's this internal differential. It has degree +1, so it increases by 1 the cohomological degree. And it has to preserve the weight, so it has weight 0. On the other hand, you have the derived differential. And the derived differential, it increases the degree also, because typically if you take a function, you take its derivative, you get a 1 form. But because of the shift that we have here, this 1 form sits in 1 more cohomological degree. So just as in the usual derived cohomology, the cohomological degree of the derived differential is +1. But it also increases the weight by 1 because we have a 0 form. Let's say a function OX that's in sim 0, and it goes in sim 1 because it gives a 1 form. So it has weights +1, right? And these two, they commute. And this whole structure, it's called a graded mixed complex. Most of you have already encountered this. Like typically, if you take a groupoid, like the first time I've seen this, I think it's in one of these paper of Pingshu, like back in the years. So if you take a smooth groupoid, so you take the nerve of a groupoid, you apply differential forms on it, you get a cosimplicial complex, and then you take its totalization. It gives you a double complex, and up to some shifting degree, this graded mixed complex that I'm talking about, it coincides with this double complex that you can find in these papers. It's just that we have different conventions from the differential. That's why they have a double complex and we have a graded mixed complex. But that's not a big deal. That's really a difference of convention. That's essentially a graded mixed complex. It's a kind of double complex, if you wish. All right. So now let me give you the definition of an n-shifted symplectic form on X. So an n-shifted symplectic 2 form on X. Sometimes I probably just say n-symplectic structure. So I drop the shifted and the form. I just say n-symplectic structure. So it's the following data. So like one way of phrasing this is say that it's a 2 plus n cocycle in a certain complex. This complex is, you take the Durand complex, you only care about the weight greater or equal to 2 parts. And actually, you don't take the direct sum of all weight space, but you take the direct product. So you take a completion. And then as a differential, you take the total differential given by the internal one and the derived one. You just take the total differential, right? So this is, I mean, taking the weight 2 and above part, that's stable by both differential because one of the two differential preserves the weight and the other one increases. So that's fine. Very concretely, that means that we have a, so that, yeah, like maybe let me for a moment to talk about a shifted symplectic structure. It is such a 2 plus n cocycle plus satisfying some non-degeneracy condition. So for the moment, let me leave aside this non-degeneracy condition and spell out completely what it means to be a 2 plus n cocycle in this complex. So to be a 2 plus n cocycle in this complex here, what does it mean? It means that you have a series omega 0 plus omega 1 plus omega 2 plus etc. So omega 0 is something of weight 2, omega 1 of weight 3, omega 2 of weight 4, and so on. Like the cohomological degree is 2 plus n, that is fixed, okay? And now if you look at the equation, it means that the internal differential of omega 0 is 0. Just if you look at weight by weight what it says. So it means that omega 0, it's not only an element in the complex of two forms. It means that it's a cocycle in the complex of two forms. So it's a globally defined two form on our geometric object. And then the next equation is that the RAM of omega 0 plus internal of omega 1 is equal to 0. So this is telling you that omega 0 is actually closed up to some homotopy, and this homotopy is given by omega 1, right? But omega 1 itself, it's not anything. Omega 1 itself, the homotopy is closed under the RAM differential up to some higher homotopy, which is given by omega 2, and so on. So somehow, like this definition, which is a bit abstract, it unravels into saying that you have a two form which is closed under some specified higher coherent homotopy, right? So that's like, if you know about L-infinity algebras, that should be very familiar to you. And then because omega 0 is a two form that is closed under the internal differential, so omega 0, it's a two form of a certain degree. So it gives you a map. So omega 0 defines some map from the cotangent complex to the tangent complex. And because of the degree, I mean, you can check that this map is a degree n map. And because it's closed by an internal differential, it means that it's a cochain map. And the non-degeneracy condition is asking that this cochain map is actually a quasi-isomorphism. So non-degeneracy means by definition that this map is a quasi-iso, right? So if you've already seen like QP manifolds, or like you've probably encountered symplectic structures on some gadgets of the same type as what I'm talking about. In most of the papers where you had this before the foundational paper of Pantaevto and Vaki and Vedzosi about shifted symplectic structure, they would always have a non-degeneracy condition that was very strict, namely that the map would be an isomorphism of complexes or something similar. And that's usually bad for like if you work up to homotopy, because if you change model of the same space, the non-degeneracy condition, if you take the strict one, it might not be preserved. The fact that the non-degeneracy condition is now phrased as something being a quasi-isomorphism, that's completely homotopy invariant. So that does not depend on the model you've chosen for your space. So that's one first thing. And there's a similar thing about the definition of a closed form as something which is closed up to higher coherent homotopies. Because if you ask like only that omega 0 is strictly closed both by the internal and by the derived differential, again, if you change model and you try to do some homotopy transfer, you will naturally end up with having something with higher coherent homotopies. All right, so let me give you a bunch of examples of such a thing. So I'll list some example. I'm not going to show and to give explicitly how like the two forms. That would take a bit too much time, but let me just state a bunch of space that we know that they carry some shifted symplectic structure. So the first example is if G is a reductive algebraic group. If you prefer, let's take a compact Lie group if you work in differential geometry. Let's pick some symmetric invariant pairing that is non-degenerate in the usual sense. Namely that it gives an isomorphism between G dual and G. Then this induces two shifted symplectic structure on the classifying stack of G that is the quotient of the points by G. All right, so I'm seeing that there's a question, that there's a comment in the chat. Oh, Ezra is saying that this construction, so I don't know when this was posted, so I don't know. The construction of the derived context the construction forms on the nerve of a groupoid. Is that correct?
Exactly. Yeah, yes. Yeah.
So it's from a paper of Botschulman and Stashev. Okay, thank you very much. Right. So now there's another thing. If you have a groupoid G1, G0 like this, and every quasi symplectic groupoid structure on this induces a one-shifted symplectic structure on the quotient G0 mod G1. So actually these shifted symplectic structures, somehow they were known, some of them were known to people doing Poisson geometry from quite some time, not under this name. So a lot of these things appear as examples of shifted symplectic structures. Let me actually mention that if, like with good assumptions like G1 to G0, it's a smooth groupoid. Then you can actually show that one shifted symplectic structures on G0 mod G1 are exactly the same as a quasi-symplectic groupoid structure on the groupoid itself. Right, and there's like, as an example, of this example, there's two things you can think about. There's a quasi-symplectic groupoid, which is actually a symplectic groupoid, which is the coadjuvant action groupoid. Then for this, you get that G dual mod out by G. That is one shifted symplectic. And this is not very much surprising because you can show that this quotient space is actually the shifted cotangent of the classifying space of BG. And this also has a one shifted symplectic groupoid, one shifted symplectic structure just because it's a shifted cotangent. Any cotangent is symplectic, and any n-shifted cotangent is n-shifted symplectic. All right, so that's one example. And there's another example. If we assume that G is reductive, then on the adjoint, on the conjugation action groupoid on G, there's the quasi-symplectic structure. And so we get on G mod G, a one-shifted symplectic groupoid structure. It's actually known that this one shifted symplectic structure can be obtained in another way, namely, this G mod G stack, it can be obtained as a mapping stack. It's mapped from what I like to call S1 Betty. So that's, if you prefer, that's the classifying stack of Z to BG. And there's a theorem of Pantev, Toenvaki, and Bezzosi, which is a kind of reminiscence of the AKZ procedure, which is telling you that if you have an n-shifted symplectic structure on the targets, so in this case, BG is 2-shifted symplectic, and if you have a space with some good notion of orientation, so here, I think you would believe me that S1 is 1-oriented. What you can do is you can pull back the form by the evaluation and then integrate over the fundamental class of your oriented guy, whatever that means, and get, in this case, a 2 minus 1, so a 1-shifted symplectic structure, which actually coincide with the one coming from the quasi-symplectic group 8. So like the more general thing, if you have something which is k-symplectic in the targets, and n-oriented in the source, by transgression, you get on the mapping space something which is k minus n symplectic. So an example of this is you would do like map from the Betty stack of some surface to BG. That would give you something which is 0-shifted symplectic, and map from the Betty stack of a surface to BG. That's the thing that that's the stack that classify G local systems on sigma, and that is something known. Like that's the that's the Atiyah-Bott. You would have the Atiyah-Bott symplectic structure on this space. Well, so the Atiyah-Bott symplectic structure is defined as the smooth locus of this space. So we have like maybe a stack which is like very not smooth. This guy is 0-shifted symplectic. It actually has an open zero smooth. It has an open smooth inside it, and when you restrict to this, you get the usual Atiyah-Bott symplectic structure on the smooth locus of the space of local systems. All right, so that's one. These are the examples I wanted to talk about, and I think that's enough for examples. Other questions so far? All right. So I'll move on to talk about Lagrangians, and I mean Lagrangian morphisms. So, like in differential geometry, Lagrangian morphism, that's something when you restrict the symplectic structure, it gives 0, and it's maximal in some way. It's a bit difficult to phrase this maximality condition in the derived setting because we want everything to be homotopy invariant. Also, it's not that easy to phrase what it means to be a sub thing, a closed submanifold, for instance. So we've taken the decision, or like people have taken the decision to talk about Lagrangian structures on morphisms. We don't care that the map is an inclusion. There are marginal morphisms which are Lagrangian, which are not given by inclusion. So let's start with a map. Let me call this F, a map between derived stacks. And I want to talk about what it is to be what is a Lagrangian structure on such a map. So let me fix omega, an n-shifted symplectic structure on X, and a Lagrangian structure on F. So like strictly speaking, I should say that's a Lagrangian structure relative to this symplectic structure omega. it's a homotopy between the pullback of omega to L and 0. And that's this in the complex of forms of weight at least 2 on L. So concretely, it means what? So omega is a cocycle in the derived complex of X in this truncated derived complex. When we pull it back to L, it gives also a form, a closed to form a cocycle in this complex. And we just want this cocycle to be exact. And the Lagrangian structure, it's the term that gives you the exactness. So we want, essentially it means that we want, so here we have what I would call the homotopy. It means that F star omega, which is F star omega 0 plus F star omega 1 plus etc. That's a series. We want it to be exact under the total differential. So we want it to be d derived plus d int of some eta, and this eta itself is a series. So then you can spell out like what it means, like term by term, weight by weight. It gives you equations. So if I just say this, it's not a Lagrangian structure. That's what you would call an isotropic structure. So I'm just saying I pull back my form and I want it to be not exactly 0, but just homotopic to 0. And I want to remember the homotopy itself. Like the homotopy is part of the data. Now, what's the non-degeneracy condition or the maximality condition, if you want? So let me add that there's a non-degeneracy condition that I want to explain now. So let me explain this. So let's rephrase what happens in the usual case. Okay, so in the usual case, what do we have? We have the tangent to L. It sits inside the pullback of the tangent to X. Because the form is symplectic, omega gives us an identification between the tangent and the cotangent. And then we have the transpose of the inclusion of the tangent of L into the tangent of X. That's a projection to the cotangent of L. And because the form is equal to 0 when I restrict it to L, this composed map is equal to 0, right? Now saying that L is maximal, it means that the map from the tangent to the conormal is an isomorphism. Another way to rephrase it in a more homological way, it is saying that this sequence is exact. And that's completely equivalent. That's a rephrasing of the condition of maximality for Lagrangian submanifolds. But that's the condition that I want to take because that's the one which is easily like generalizable to like a more homotopical setting. And what we're saying is that now we have the tangent to L. It goes to the pullback to the tangent to X. Then we have omega that gives us some map to the cotangent with some shift because omega is now a shifted form. We know that this map here, it's a quasi-isomorphism. So it's, I mean, like from the homotopy perspective, it's irrelevant. I can deal with the pullback of the tangent or of the shifted cotangent as if they were the same. And then there's the map to the cotangent of L. And because I know that the pullback of omega is homotopic to 0, in particular, I know that this sequence, this sequence here, it's a null homotopic. It means that the map from TL to the cotangent of L with a shift, it is homotopic to 0. And the non-degeneracy condition is saying that not only it's null homotopic, but we want it to be a homotopy fiber sequence. In other words, so if you're if you prefer to deal with like derived categories, it's saying that this triangle is an exact triangle. Or if you're more confident with like more down-to-earth homological algebra, we're just saying that this map induces a long exact sequence in cohomology, right? So let me give you a bunch of examples of Lagrangian structures. Okay, so the map from G dual to G dual mod G. So we've seen that G dual mod G is one shifted symplectic. This map is Lagrangian. That's one example of a Lagrangian structure. The map from point mod G, namely BG, to G dual mod G is also Lagrangian. So these are like the second one, it's more familiar and more like the usual thing. It seems like a sub-object, but the first map, the first one, the first example, it's not a sub thing. Like it's rather like something subjective. It's an effective epimorphism. And so it makes sense to have Lagrangian which are not sub-objects. So that's one interesting thing. A really cool example is that if we have, let me call this mu, we have, so we assume that X itself is symplectic and it comes with a moment map. So X is symplectic, there's a Lie group acting on X by symplectomorphism, and there's a moment map for this Hamiltonian action, right? Then the induced map between the quotient stack is also Lagrangian. So that's an interesting thing that moment maps leads to Lagrangian structures on the quotient map. So on the map between the quotient stacks. And actually with good assumption, Lagrangian structure on such maps are actually exactly the data of a symplectic structure on X together with the moment map property. There's a similar thing if you have like a map like this. What's the name? If you have a Lie group valued moment map. Then the induced map from X mod G to the conjugation action, the quotient by the conjugation action, that's also a Lagrangian morphism. And finally, the last example I want to give, it's a weird example. That's an extreme case that people would never think about if they think about sub-objects. So if you take the points, on the point, there's just one n-shifted symplectic structure, which is 0. So you take omega being 0, it's n-shifted symplectic. And you consider the Lagrangian structures on the map from X to the point. These things are in one-to-one correspondence with n-1 shifted symplectic structures on X. That's a bit of a weird thing. It is just because like we have a, so if you think about it, if we forget about the non-Jurassic condition for a moment, what it means to have a Lagrangian structure. So we pull back 0, it gives 0, and we want it to vanish up to homotopy. So we want a homotopy between 0 and itself in the space of n cocycles. So we want 0 to be equal to d eta. So it means that eta is an n-1 cocycle. And then you have to check that the non-adjacency property is the same on both sides, right? So like this example is super cool because it has a nice feature. This nice feature is that because we can talk about Lagrangian morphism, we can also talk about Lagrangian correspondences. So we can talk about Lagrangian correspondence. So if you have X and Y symplectic, I will write a Lagrangian correspondence between X and Y, it's just a Lagrangian morphism to x cross y. But when we have like the symplectic form, which is given by omega on x and minus omega on y, right? And now if you have another correspondence between y and z, we can take their fiber product. And that's also a correspondence, which is also Lagrangian. So that's something you're used to. Usually in differential geometry, we would impose some transversality conditions so that we get something non-degenerate in the ends of the correct dimension. In the derived setting, if you take the homotopy fiber products, you don't have to care about this. When you compose Lagrangian correspondence, you get Lagrangian correspondence again. That's one of the cool thing of doing things, of working with derived geometry. The bad thing is that you have to, like, it's much more technical and you have to deal with a bit more pathological spaces. But as an example, if you take x and z to be points, Lagrangian correspondence are just Lagrangians in y. And so when you compose like this, what you do is you just intersect, like, yeah, I should say intersect in quotes, because it's just a fiber product between L1 and L2 over y. And that gives you a correspondence between point and point, which means where point is n-shifted symplectic. So it means that you get an n-1 shifted symplectic structure on Lagrangian intersections. So if you intersect or do the fiber product of Lagrangians in or towards an n-shifted symplectic guy, you automatically get an n-1 shifted symplectic guy. So there's a bunch of example of this that give back a lot of things that we know about symplectic production. So the first example, if we have a moment map, all right, so now we know that this gives us a Lagrangian structure, a Lagrangian morphism towards this one-shifted symplectic quotient G dual mod G. So how on earth this Lagrangian structure does it know about the symplectic structure on X? Well, we can intersect it with the Lagrangian, which is G dual goes to like this Lagrangian I talked about before. When we do this pullback, that gives back X. So we've intersected two Lagrangian in or towards a one-shifted symplectic guy. So this gives us on the intersection, which is X, a zero-shifted symplectic structure. So somehow the Lagrangian structure on these morphisms, on this morphism given by the moment map, it carries the information of the symplectic structure on X, just by pulling back along this quotient map. You can also recover the reduced space. If we do intersect BG, so BG is point mod G, what we get is the fiber product of X with point over G dual mod G. But fiber product of X mod G with point over G dual, that's exactly taking mu inverse of 0, maybe in some derived way. So that's actually doing it in a derived way. It means that you have to take some Kosovo resolution. And that's the very reason for the appearance of these variables YY, Y1, YK that I was talking about in the very beginning of the talk. They actually come from taking the zeros in some homotopy way of the moment map. Right, so there's this nice feature that by doing derived Lagrangian intersection, we completely kind of like recover like this usual thing of symplectic production. We can have a bit more. Actually, we can also recover the fact that mu inverse of 0, again, that's the derived 0. It has a So let me call this X red. So it has a map, a quotient map to X red, and it has a map to X. And that's you can show that that's a Lagrangian correspondence. So this is also something that is known, right? Like in differential geometry, under some assumption, when everything is smooth, that is something that is very well known. All right. Nikita, just a question. How much time? Like I didn't ask you how much time the talk was, so I assume it's 1 hour, but I don't know.
So yeah, the talk is 1 hour, so you have 10 minutes, but to mimic Anton Alexeyev, it's negotiable.
Okay, I'll try to make it in 10 minutes.
All right.
All right. Another nice Lagrangian intersection is the following. So you take the cotangent to X, you take the graph of the differential of a function, or the graph of a closed one form is perfectly fine. That's an example of a Lagrangian. You can also take the zero section. That's another example of a Lagrangian. And when you do the intersection, if you like, you get what should be called the derived critical locus of F, right? That's just the zero locus of df. And because these two things are Lagrangian, and X is T star X is zero shifted symplectic, this derived critical locus becomes -1 shifted symplectic. And now, like, again, we're taking the zeros of something. If you do it in a homotopical way, that's adding this variable xi1, xik, xin, sorry, that I was talking about in the very beginning. Again, these are Kosool generators. Okay. Now, here's the main theorem I want to. So now here's the main theorem I want to state, which is this result I proved with Mathieu Anel. So again, we have X, we have a function on X, we have a group G acting on X, and F is G invariant. So if we're in a situation where we have like more homotopies and etc., being invariant, it might actually be some more structure and not only a property, but it doesn't matter so much. What I need is that the invariance data is just the data of a function that descends to X mod G. So this G invariance, even if it's a property, that's just equivalent to the data of some F red that goes from X mod G to A1, and which is such that when you compose it with the projection from X, you get F. So we should take this F red as part of the data we start with. All right. So the theorem says two things. So first of all, it says that there exists a moment map from the derived critical locus of F to a shifted version of the dual of the Lie algebra, such that when I do the symplectic reduction of this, I get something which is the derived critical locus of F red as -1 shifted symplectic stacks. And that's exactly what I said in the beginning. So let me, I need to go back to the beginning to just remember what was the A side and what was the B side. All right. So yeah. So that is really A, and that is B. So I didn't tell you exactly what's a moment map with value in G dual shifted by -1. But like if you go back to the example we had here, I said that a moment map, like a usual moment map on X, that's equivalent to a Lagrangian structure on the map from X mod G to G dual mod G. So a moment map from X to G dual shifted by -1. I just declare that's now a definition. That's the same as the Lagrangian structure on this. So I will say that there is a moment map here. That's the exact same thing as saying that we have a G current map from X to G dual shifted by -1, and we have a Lagrangian structure on the map between the quotients, right? And now the reduction of such a thing, that is just defined in the same way as what we did here. If you have X mod G goes to G dual shifted by -1 mod G, the map from BG, it's also Lagrangian. And again, the reduced -1 shifted symplectic structure, that's gonna be just the fiber product here. Just in the very same way. So like what we've done is we've reinterpreted like all the business of symplectic reduction in terms of Lagrangian and Lagrangian intersection. And now for the shifted version, we take this point of view of Lagrangian and Lagrangian intersection as definitions of what these are. All right, so like I won't give the proof of this, but I want to explain why there is a moment map like this. So why on earth there's such a map here from the critical locus of F to a shift of G dual? And that's something we can explain very easily, actually. So we have the critical locus of F. It's the intersection of the zero section in the cotangent and the graph of dF. And now observe that the cotangent itself, it has a moment map, right? And the fact that, well, first of all, the zero section, it factors through 0. Well, that's pretty obvious when you apply the moment map. And now the fact that F is invariant, it also tells you that the graph of dF, when you apply the moment map, you get 0. That's just invariance of F. So it means that the intersection of the zero section and the graph of dF, which is here, it factors through the intersection of 0 with itself in G dual. And if you think about what it is, that is exactly G dual shifted by -1. If you remember a bit of like, I don't know, it depends on your background culture, but if you like typically in homological algebra, if you want to do the homotopy fiber product between 0 and 0 in a, let's say in a cochain complex, 0 to a cochain complex, that's not a fibration. So you're gonna replace 0 by some equivalent complex which has 0 cohomology, but which fibers over V. So you're taking the cone of the identity, for instance, you're taking V plus V shifted by -1, and you're taking the identity as a differential. So yeah, let me write this. So we have 0 goes to V, 0. I'm just saying that 0 is equivalent to V plus V shifted by 1, where the differential is just the identity from V to V shifted by -1, right? So because we're taking homotopy fiber product, replacing by something equivalent that doesn't change the results. But now the map from V plus V shifted by -1 to V, that's a fibration. So the homotopy fiber product, when one of the factors is a fibration, you can take the strict usual fiber product. So now if you take the strict fiber product, it kills this V factor here. and you end up having V shifted by -1. That's the usual calculation of like the loops in a stable category, for instance. There's a comment somewhere. Yes, Dima, that's exactly, that's the, we're computing the loops, the base loop space of zero at 0 in V, exactly. All right, so that's where this moment map come from. And you can observe that actually all what I've been saying has not much to do with the critical locus. If you take the derived intersection of two Lagrangian, which are kind of equivariant with respect to some moment map, you can prove a more general statement that's, so let me like end the talk with this. So if we have L goes to X, L1 and L2, two Lagrangians in X, assume that X gets a moment map, and assume that these Lagrangians are reducibles. Reducibles means that they factor through 0 by the moment map, right? So if L1 and L2 are reducibles, then what we get is that on L1 cross L2 over X, with the same procedure, there's a shifted moment map. And when we compute the -1 shifted symplectic reduction of this, we get the same thing as taking L1 mod G, L2 mod G, intersecting them in X red. So that's a fact that if L1 is reducible on the quotients L1 mod G, it has a map to the reduced to the symplectic reduction of X, and this map is still Lagrangian. So somehow we have a kind of commutation relation between Lagrangian intersections and symplectic reduction in some way. And the theorem I stated that we've proven with Mathieu is just it's just an instance of this. Sorry, I'm over time by a few minutes. I'm finished. Thank you very much.
That's okay. Yeah, thank you, Damien, for a wonderful talk. Are there any questions?
Could you go back to the last slide, please? Just show us the end.
Oh, yes, here.
Okay, thank you. Again, reducible means what exactly?
Oh, so reduce means this this procedure that let me call so let me call this intersection, let me call this M. So this M has a map to G dual shifted by -1. So part of the statement, it says that this is a moment map in some way. So it says that there's a Lagrangian structure on the map between the quotient stack. So that comes with a Lagrangian structure. And now I can intersect it with point mod G. And that's what I'm calling the reduced guy. So like essentially that's taking 0 of the moment map and modding out by G. That's what it does.
Mm-hmm.
But now the moment map takes values in some shifted guy and not in value, like it takes values in G dual shifted by -1. So like typically when you have when you have an honest moment map, when you take zeros in a homotypical way, you have to take a Kosool resolution. So you will add generators in degree now -1. But now if you have a moment map with values in a space shifted by -1, doing the same trick will give you new generators of degree -2. And that's the eta 1, eta k I was talking about in the very beginning of the talk. So the generators eta 1, eta k, I was mentioning in the beginning of the talk, they occur when taking the derived zero of such a moment map mu with values in a shifted version of the dual of the Lie algebra.
Thank you very much. But my question was even more basic than that. What does it mean for a Lagrangian to be reducible?
Oh, to be reducible. Yeah, so like the correct definition is, okay, so L to X. So now X is symplectic. The map is Lagrangian. We say that this is reducible if there exists L bar. So, and we have to assume that there's a moment map on X, right? So that's part of the data we start with. So we say that L to X is reducible if there exists a Lagrangian, let's say L bar to X red. Let me call this L red, that's better. Okay, such that, so we have this Lagrangian from L red to X red. And now remember that we have X and we have, this is a Lagrangian correspondence between X red and X, right? So I view my Lagrangian in X red as just a correspondence between point and X red. Okay. And I want that when I compose these two things, it gives back the Lagrangian L in X. So that's what it means to be reducible, strictly speaking. So it means that there exists an L red such that when I compose, I get back L. If you work a bit, you can prove that, forgetting about Lagrangian structure, L red has to be the same thing as the quotient of L by G, first of all. That's one thing. So that's a consequence of the definition. And if you specify the definition where everything is smooth, Lagrangian really means Lagrangian submanifold, then so if we're in the situation where X red is smooth, X is smooth, this is smooth, and L is smooth, and the map from L to X is a closed embedding. So we're like in the better situation we can hope for. Actually, so this L red is L mod G. And first of all, the map to X red has to be an inclusion. And being Lagrangian becomes no more a structure, but it's just a property, just like in the usual. So in some sense, being reducible, that's additional data. But in very nice situation, that's not additional data. That's just a property. But just like in the derived setting, being Lagrangian, that's additional data. That's not a property. But when you boil down to the usual thing, when you have a smooth submanifold in a smooth manifold, that becomes a property, being Lagrangian, and no more an additional structure.
So is it the derived way of saying that your Lagrangian is contained in the zero fiber?
Exactly. That's exactly this. Yes.
Okay. Thank you very much. Thanks.
Sorry, I should have started with this.
Thanks.
Okay. Any other questions?
May I?
Yeah.
Yes.
Go ahead, Dima.
Well, thanks for a very nice talk, first of all, Damien. So I just wanted to say that I was always mystified by this fact and this in the BV procedure that, well, whereas the function f, the critical locus of the derived critical locus of the function f you start with is quasi-smooth. But the derived critical locus of f reduced is not.
No, it's not.
Because you have these anti-fields of the ghosts, and
right.
So in answering the previous question, I think you just demystified this for me, because, they appear as this the derived zero of this shifted momentum map.
Right.
So
yeah, it's also because also when you there's this thing that's so if you start with an honest manifold and you do the derived critical locus, you get something quasi-smooth. But of course, if you start with something which is already a stack, which is already like a there's no reason for the critical locus to be quasi-smooth. That's true, and like with this result, it kind of explains somehow why. I agree.
Thank you. Thank you very much.
Okay, any more questions for Damien? If there are no more questions, then let's thank Damien one more time.
Thanks.
And we'll see you all back here in 2 weeks for our second global Poisson of the semester. All right, bye-bye everyone, thanks.